Welcome back to the Deep Dive. If you joined us for our foundational discussion, you've got the essential vocabulary of API management down. The what, the how, all the building blocks. But today, we are definitely leveling up. We're moving entirely into the architectural side of things.
Right.
Take a really serious look at the tools, the tech, and I think most importantly, the why behind choosing one complex platform over another.
That's it, exactly. I mean, for anyone who's moved past a simple API key, you realize pretty fast that the architectural landscape is, well, it's a maze.
A dizzying maze, yeah.
And you start facing these really high-stakes questions. Do you stick with a simple, cost-effective API gateway?
The easy route.
The easy route, yeah. Or do you need to specialize with something like cloud endpoints? Or, and this is the big one, do you commit to a massive enterprise platform like Apigee?
And these aren't small decisions. I mean, they're driven by budget, right? By performance needs, and as we'll get into, some really serious regulatory constraints.
Non-negotiable ones, often.
And that really defines our mission for this deep dive. We want to take all those fuzzy concepts and make them solid. We're focusing strictly on that API platform layer, and we're going to be using some analogies today.
Yeah, the analogies are key. We're going to talk a lot about traffic management, a bit of urban planning even.
I like it.
Just to make these abstract ideas like policy enforcement really land for you.
So we'll start simple. We'll look at the leanest gateways, the ones built for speed and light work. And then we'll pivot to the heavyweight, to Apigee. We'll really dissect its advanced capabilities for controlling traffic, for security, and even for turning APIs into actual revenue.
Let's do it.
Okay, let's unpack this.
Yeah.
We have to start with this foundational truth. Not all APIs are created equal. If you're building a simple modern backend, you do not need a billion-dollar platform.
Oh, absolutely not. That's overkill.
So the first architectural choice is really distinguishing between simple routing and full-scale enterprise governance. What does that entry-level landscape even look like?
Think of the gateway as the front door to your digital house, your infrastructure.
Okay.
And when you look at the options, you have to decide what kind of front door you need. Is it just a simple mail slot?
Right.
Or a basic security turnstile? Or do you need a full airport security terminal?
Right. And that choice dictates everything. Latency, complexity, and definitely the cost.
And the operational overhead. That's a huge one for modern dev teams.
Let's start with that lean, fully managed option then. The basic API gateway. Our source material gives us a super clear use case for this.
Yeah.
Imagine you've built a modern serverless backend, let's say 5 microservices, all deployed on Cloud Run and Cloud Functions. It's fast, it scales, it's cost optimized, but you need a single public address for all of them.
That is the perfect sweet spot for a general API gateway. The core requirement here is just simplicity and complete management of the infrastructure, plus tight cost control. The reason you choose this, the why, is really the absence of those big enterprise needs.
So you're just trying to consolidate URLs.
Exactly. Take those 5 messy URLs, put them behind one clean public entry point, handle some basic API key authentication, and just route the requests. That's it. You don't want to be patching servers.
Okay, so when we say fully managed, let's dig into that. For a small team, what does that practically mean they're not doing anymore?
It means they're not doing the tedious operational stuff. The provider is handling certificate rotation, they're patching the underlying OS, they're scaling the gateway layer up and down to handle the load, they're even handling DDoS mitigation.
That's a massive amount of time saved, isn't it?
It's huge. The savings are in OpEx and, maybe more importantly, in engineering focus. Your team can focus on building features, not managing infrastructure.
And the cost model is different too, right?
Totally different. It's purely usage-based. You pay per request, you pay for the data you transfer. There are no huge upfront license fees, no monthly commitments for servers you might not even use.
It scales to 0.
It scales down to 0. If you get no traffic, you pay nothing. It's the ideal path for teams that need to be agile and, really cost-conscious.
But there's always a trade-off. If I'm choosing this simple API gateway, what am I specifically giving up? What are the crucial exclusions I need to be aware of?
Okay, the exclusion list is what defines this choice. You are giving up deep, customizable policy enforcement. You don't get those sophisticated real-time analytics dashboards.
Okay.
And this is the big one. You do not get built-in monetization engines. If your business plan is to sell your API with those silver, gold, pay-per-use tiers, this simple gateway just won't cut it.
So you choose it because you don't need that overhead.
Precisely. It's the simplest, most cost-effective tool for that very specific job, routing and basic auth.
That sets a really clear boundary. Now, Let's turn the dial up on performance. What happens when simplicity is secondary to raw speed? And you're using, well, highly specialized protocols. That brings us to our high-performance specialist, cloud endpoints.
Right. Cloud Endpoints lives in a very specific niche. It's almost always about supporting gRPC services.
Running on container platforms like GKE, Google, Kubernetes Engine.
Exactly. If you're building modern microservices today, especially for internal communication, the default is shifting away from traditional REST and JSON and towards gRPC.
Okay, we have to pause here. gRPC. A lot of our listeners will know REST and JSON inside and out.
Yeah.
Why is gRPC the high-performance choice? What is it, really?
So gRPC stands for Google Remote Procedure Call. It's an open source framework built for pure efficiency.
Unlike REST, which is text-based.
Right. REST APIs use JSON, which is human-readable text, over HTTP 1.1. gRPC uses the newer HTTP 2 protocol, which is already a big step up. But the real magic is in the data format. It uses something called protocol buffles.
Or protobuf.
Protobuf, yeah. Can you give us an analogy? How is protobuf different from JSON? I like to think of JSON as a formal letter. Every piece of data comes with a full description. You have first name, Alice, order it, 1, 2, 3, 4, 5. You're sending all those descriptive words, the field names, with the data every single time.
Which adds up.
It adds up a lot. Protobuf, on the other hand, is like, it's like a pre-printed form where both sides already know the layout.
Oh, right.
The sender and receiver have agreed ahead of time that field number 1 is the first name and field number 5 is the order ID. So don't send the descriptions, you just send the raw data.
It's just the bits.
Just the bits. It's a binary serialization. And that means the messages are way, way smaller, sometimes 10 times smaller. And they're much, much faster to parse. That's why it's the default for high-speed internal microservice communication.
Okay, so gRPC is amazing for internal performance. But here's the problem I see immediately. External partners, web browsers, mobile apps, they all still speak the language of the web. They speak HTTP and JSON.
Yep.
So how do I bridge that gap? How do I get a standard web request to talk to my super optimized gRPC backend?
And that is the exact problem Cloud Endpoints was built to solve. It has a feature called gRPC transcoding.
It's an interpreter.
It's a high-speed, automatic interpreter. An external client sends a totally normal HTTP request with a JSON payload. Cloud Endpoints catches it, it understands the destination is a gRPC service, and it automatically translates that request into the compact binary protobuf format.
And it sends that tiny, efficient request to the internal service. And I assume it reverses the process for the response.
You got it. The backend service never even sees JSON. It only ever speaks gRPC. Cloud Endpoints gets the protobuf response, transcodes it back into standard JSON, and sends it back out over HTTP to the client.
So you get the best of both worlds.
You get the internal speed of gRPC without losing compatibility with the entire web ecosystem.
That sounds computationally intensive, though. All that translating and serializing on every single request must add some overhead, some latency.
It does. And if speed is your absolute priority, you have to minimize that latency. That's where the deployment model for Cloud Endpoints becomes so important. It runs as a sidecar container.
Okay, a sidecar. That means it runs right alongside the service it's protecting, not in some separate, centralized gateway layer.
Exactly. It's typically deployed in the very same Kubernetes pod as the application service. Imagine 2 containers in the same little box sharing a network connection.
So there's no network hop to a central gateway.
None. The communication between the Cloud Endpoints container doing the transcoding and the actual gRPC application is instantaneous. It's local loopback. It minimizes that added latency to the absolute theoretical limit.
So that architectural choice, the sidecar model, it's all about speed. You're trading some centralized control for the lowest possible latency.
That's the trade-off. It's purpose-built for that high-performance, containerized gRPC niche.
Okay, that's a perfect summary for this first section. On one hand, the simple API gateway for serverless, prioritizing simplicity and cost. On the other, the specialized cloud endpoints, prioritizing minimal latency for gRPC. But now we have to talk about real governance.
Right, because at some point, budget and simplicity are no longer the primary drivers. Governance, security, monetization. When those become the top priority, the whole architectural decision changes.
And that's when we have to step into the big leagues. When a company's needs go way beyond simple routing. When you need full-stack governance, data residency, complex business logic, you enter the world of enterprise API management.
And that world is dominated by platforms like Apigee.
So Apigee isn't just a router.
Not at all. It's an entire ecosystem for what you'd call API product management. It's the answer you need when you You hit the scaling and security limits of a simpler gateway.
What defines that full-featured requirement? What's the trigger that makes a company say, okay, we have to bring in this heavyweight, which, let's be honest, comes with a much higher price tag?
It's the sheer breadth of the capabilities and the need for them to work reliably at a massive scale. We're talking about things that turn an API from just a technical endpoint into a secure, controlled, and revenue-generating product.
Like what specifically?
Well, first, comprehensive governance. Managing hundreds, maybe thousands of APIs with consistent security, documentation, and versioning. Second, advanced policy injection.
Which means?
The ability to inject custom logic transformations, security checks into the request path without having to change your backend code.
That's powerful.
It's incredibly powerful. Then you have complex rate limiting and traffic shaping. And finally, the built-in monetization and developer portal features. Those are the big ones.
To make this huge concept feel more concrete, let's use our main analogy. We're framing Apigee as the ultimate traffic controller and security checkpoint.
This analogy is so important because it gets to the core problem Apigee often solves, dealing with fragile legacy systems.
Okay, explain that.
Imagine your company's core backend systems, maybe decades-old mainframes, proprietary databases, as a historic, beautiful, but extremely sensitive city center.
I'm with you. The roads are cobblestone, the buildings are delicate.
Exactly. These systems are invaluable, but they were never, ever designed to handle the pure chaos of modern internet traffic. The billions of requests, the security threats, the sudden massive bursts of load.
And if you let that modern internet traffic slam directly into that sensitive city center, the whole thing just collapses.
It grinds to a halt. And that's your core business functions freezing up. So Apigee positions itself as this highly sophisticated traffic control system that you deploy just outside that vulnerable city.
It's a buffer.
It's a mandatory buffer and a policy enforcement layer. The traffic controller's job is not just to route traffic, but to shield the city. It takes the full brunt of the modern internet. It handles all the messy stuff, security, authentication, protocol translation, before it lets a gentle, safe, controlled stream of requests into the fragile internal systems.
So it's not just directing traffic, it's mediating it. It's translating the chaos of the web into a polite, predictable conversation that the old legacy system can actually understand and handle.
Precisely. And the enforcement part is crucial. Every incoming request gets its passport checked, the API key, the OAuth token. The system checks if you're allowed on that particular street, access that resource, and it meticulously checks your speed and how much you're carrying.
That's rate limiting in quotas.
Exactly. It makes sure that one single runaway app or a malicious user can't bring down the entire legacy infrastructure. It ensures stability for the whole enterprise.
And that lets the core systems keep doing what they do best, without needing massive, expensive rewrites.
You've got it. That's the core value proposition.
Okay, the moment we introduce that buffer, that controller, it opens up the next big topic. The nuance of managing traffic flow. How does Apigee tell the difference between a user who's consuming a service normally and one who's about to crash the whole system by accident?
And that brings us to maybe the most vital distinction in API governance: consumption limits versus infrastructure protection.
Yes. This is where we separate the intermediate listener from the beginner, because most people just hear rate limiting and think it's one thing.
Right.
But in an enterprise platform, the difference between managing the customer's contract and protecting your own hardware, that's everything.
Let's start with the easier concept first, the quota policy. This is fundamentally a business and accounting tool.
So the quota enforces an overall volume limit. How many calls you get over a long period, like a day or a month.
Exactly. Think of it as a pool of available requests that's tied directly to what the user is paying for. If they're on a plan that gives them 10,000 calls per day, the quota policy just keeps a running tally.
And once they hit 10,000, they're cut off.
They're cut off until the quota period resets, maybe at midnight or on the first of the month.
This is the data allowance on your phone plan. It's all about total volume. But, and this is the key, that total volume, if it all arrives in 1 second, is what actually crashes things.
And that's why you need the second tool, the spike arrest policy. Let's go back to our problem scenario. You've got a backend database, and you know for a fact it has a hard limit. It will crash if it gets more than 100 requests per second.
Okay. And our customer has a generous daily quota of 10,000 calls.
They are perfectly within their rights to make 10,000 calls, but then they deploy a new script. Maybe it has a bug, and it suddenly hammers your API with 500 requests in one single second.
So even though their daily quota is fine, that 1-second burst is 5 times the safety limit of the backend.
And that massive instantaneous burst will crash your system. It will lock out all your users, not just the one causing the problem. Spike arrest doesn't care about the daily quota. It only cares about limiting the rate of calls right now, in this instant.
Okay, hold on. This is where I think people get tripped up. If the system can only handle 100 requests per second, why can't I just enforce a very low quota? Say 500 calls every 5 minutes. Wouldn't that solve the problem more simply?
That is a fantastic question, and it really gets to the heart of why you need both. Using a simple quota for rate control creates a bad user experience, and honestly, it's not effective for real protection.
How so?
Well, first, the bad user experience. If a user is paying for 10,000 calls a day and you put a rigid block of 500 calls per 5 minutes on them, you might prevent them from doing legitimate work. What if they need to run a batch job that makes 1,000 calls in 1 minute and then they're silent for the rest of the day? Your rigid quota stops them.
Okay. It's too blunt of an instrument.
It's way too blunt. Second, and more importantly for infrastructure, spike arrest is dynamic. It's designed to smooth out the flow. When those 500 requests arrive in 1 second, it immediately queues or denies the extra 400, ensuring the backend only ever sees the safe 100 requests per second. It protects the system instantaneously.
So quota manages the business contract, the overall budget of calls. Spike arrest is the dedicated crash prevention tool, focusing only on the real-time rate of arrival.
They work together, but they serve entirely different masters. One serves the business, the other serves the infrastructure.
That makes perfect sense. Okay, so once you have that robust traffic controller handling flow and security, you said APIs stop being just a technical tool, they become a business product.
Absolutely. And that shift requires specific platform capabilities that simple gateways just don't have.
This is where we get into turning data access into actual money.
Yes. This is why companies buy platforms like Apigee. It's about turning proprietary data into a predictable revenue stream and efficiently managing the developer community that's going to use it.
Let's start with API monetization.
Yeah.
This isn't simple. The scenario is a business wants to sell its data, but they need flexible tiers to capture the whole market.
This is a deep dive into business complexity. The platform has to handle really complex usage patterns and turn them into billing events. Look at the tier structure we talked about.
Right. You've got the free tier,
which is low volume, maybe 100 calls a day. It's for onboarding, letting people try things out. The platform has to manage these users even though they don't pay you anything.
Then you have the silver tier.
That's your subscription. High access, say 10,000 calls a day for a fixed monthly fee. The platform needs to track that recurring revenue and reset the quota perfectly on the billing cycle date.
And finally, the gold tier. This one is more complex, pay-per-use.
Right. Unlimited access, but you're charged per call. Or even more complex, maybe you're charged based on the size of the data returned or the type of transaction. A read is cheap, a write is expensive.
Managing that kind of billing logic, that sounds like a massive custom software project if I had to build it myself.
It is a profound engineering headache, and if you get it wrong, you have reconciliation errors, angry customers.
Yeah.
It's a mess. This is why the solution is the Apigee monetization add-on.
It's built in.
It's built in, and it's designed specifically for this. It handles the metering, the plan definitions, the policy enforcement, and calculating the costs. It eliminates the need to build and maintain your own fragile billing logic.
So it tracks the usage, applies the right price, and then what? Does it integrate with accounting systems to send the actual invoice?
Exactly. It bridges the gap between the network traffic happening in the gateway and the finance department. It transforms the API gateway from just a cost center into an integrated profit center.
Okay, so you have the product, you have the pricing. Now you need to get developers to actually use it. You can't onboard every single one by hand. That's where the integrated developer portal comes in.
The core need here is scale and self-service. When you have hundreds of partners, you have to give them a professional self-service channel. If your engineers are spending their time answering, where's my API key, emails, you're just bleeding resources.
So the portal is the digital storefront for your APIs.
It's the storefront and the self-service admin office. It handles the entire developer lifecycle.
What are the absolute must-have functions of that portal?
1, app registration. Developers sign up, they register their app, they tell you what they're building. 2, self-service key retrieval. This is the biggest efficiency gain.
No more emails.
No more emails. They get approved, the portal automatically provisions their API keys, and they can get started immediately. 3. Interactive documentation.
Powered by standards like OpenAPI.
Right. So it's not just a PDF. Developers can see the data schemas and, crucially, use a try it out button right in the browser. This massively speeds up their development time.
And the last one.
Usage analytics for the developer themselves. They can see how close they are to hitting their quota. They can manage their own usage without ever needing to contact your support team.
And this seems critical for managing API versioning. If you need to deprecate version 1 and push everyone to version 2, the portal is the hub for that communication.
It's the single source of truth for your entire partner ecosystem. It just offloads so much of the administrative burden, letting your engineers focus on building great OPIs.
Okay, so we have a traffic controller that's managing flow and enabling business. But when we move from general traffic to malicious traffic, standard API keys and rate limits often aren't enough.
Not even close. Security complexity scales with the value of the data you're exposing. If you're serving financial data or sensitive customer info, your APIs become a prime target for automated attacks.
And our sources highlight a very specific modern challenge: intelligent bots that are designed for scraping.
The problem with modern bots is they are smart and they are persistent. They might be trying to steal your pricing data or harvest inventory.
And they know how to get around traditional security.
Exactly. If you're just relying on a simple firewall that blocks IP addresses, the bot masters will just continuously rotate the IP address they're attacking from. Every request looks like it's coming from a brand new user.
So you're just playing whack-a-mole with IP addresses, but the underlying bad behavior is still getting through. You have to block the signature of the attack, not the address.
That's the key. And the solution here is Apigee Advanced API Security. The core of this is a shift to behavioral analysis, and that's powered by machine learning.
This is where it gets really interesting. How does machine learning solve that IP rotation problem? What is it looking for that a human or a simple rule can't see?
The system completely shifts its focus from the network address to the request signature. The ML model is constantly looking at huge volumes of your API traffic, and it's building a statistical baseline of what legitimate human traffic looks like.
Across what kind of dimensions?
Things like temporal consistency. Human traffic is a bit random. A bot might make requests with an unnaturally perfect rhythm, like every 497 milliseconds on the dot.
A human can't do that.
No. Or header consistency. Bots often use the same fake user agent string over and over. They might be missing headers that normal browsers always include. Or they might try to hit every single one of your API endpoints in alphabetical order way too fast for a person to navigate.
So the ML model is trained to spot those machine-like patterns, the too perfect or too repetitive behaviors that are hiding behind the constantly changing IP addresses.
It's hunting for anomalies. When that scraping bot attacks, the ML model sees the patterns, the perfect timing, the identical headers, and it correlates them across all those seemingly random IPs. Once it confirms the malicious pattern, it can automatically block or throttle that traffic in real time.
That feels like a huge step up from just static firewall rules. It's moving security from being reactive to being proactive and behavioral.
It has to be, because the attackers are constantly learning, so your defense has to be constantly learning too. That's a level of dynamic security you just can't get from a simpler gateway.
We've covered features, speed, business logic. Now we have to hit the ultimate driver of architecture: legal and regulatory mandates.
Yes, because sometimes the platform choice is made for you by external, non-negotiable rules about where your data is allowed to physically exist.
Right. Architecture is always a response to constraints. And when you're dealing with sensitive data, financial, health records, the question of whether that data can cross a national border can override everything else.
It overrides cost, it overrides operational simplicity, everything.
This brings us to the critical distinction between Apigee's deployment models, specifically contrasting the fully cloud model with the specialized one built for control, Apigee Hybrid.
So let's use the specific constraint from our source material. A company handling sensitive financial data has a strict data residency law they have to follow. The mandate is firm. The API runtime traffic, the actual sensitive data, can never leave their on-premises data center.
But at the same time, they want the convenience of the cloud. They want the automated updates, the scalability for management tools.
It's a classic dilemma. To understand the solution, we have to clearly define the two planes of an API management platform: the management plane and the runtime plane.
Okay, what's the management plane?
The management plane is the control center. It's the brain. It's the UI where you log in to configure all your policies, your quotas, your spike arrest. It's where you manage developer accounts and look at all your analytics dashboards.
And the runtime plane.
The runtime plane is the execution engine. It's the muscle. It's the actual server infrastructure where the traffic flows, where the policies are enforced on every single request, and where the data is passed to your backend. It's where the sensitive payload actually lives in transit.
In a normal, fully cloud deployment, both of those planes, the brain and the muscle, live in the public cloud.
Exactly. And for our financial firm, that's a non-starter. It violates their residency mandate.
Which is why they need Apigee Hybrid. So how does Hybrid solve this problem?
Apigee Hybrid is all about separation of concerns. It allows the management plane, the brain, the configuration, the analytics to live conveniently in the public cloud. So your developers get all the benefits of a modern cloud tool for governance.
But, and this is the crucial distinction, the runtime plane is deployed somewhere else.
Yes. The API runtime traffic, the actual muscle that processes the sensitive financial data, remains strictly inside the company's own on-premises data center.
So the policies are defined in the cloud, but they are executed locally, on-prem. The sensitive data itself never leaves their building?
Never. That's how they meet the strict residency law. It provides the best of both worlds. Cloud convenience for management, but ironclad control over data location for compliance.
But that control has to come with a trade-off. If I choose hybrid, I'm now responsible for running that runtime plane myself, right? I'm managing the Kubernetes clusters, doing the patching, handling the uptime.
You've just hit on the hidden cost of control.
Yes.
When the choice is driven by a mandate like data residency, that operational complexity becomes a necessary evil. You gain absolute control over data location, but you take on the responsibility of operating a pretty significant piece of infrastructure yourself.
Which is a stark contrast to the fully managed cloud model, where the provider handles all of that for you.
It's a direct, unavoidable trade-off. You're swapping operational simplicity for compliance control.
That's separation management versus runtime and the trade-off it forces. That feels like the ultimate key to understanding advanced API architecture. It's not just about features anymore. It's about jurisdiction.
We have definitely covered a lot of ground today. We've gone from the lightest touch gateway solutions all the way to these profound architectural decisions at the enterprise level.
We really have. We started with those minimalist options, the simple API gateway, chosen for cost-effective, hands-off writing for serverless, and then the specialized low-latency cloud endpoints running as a sidecar to handle high-speed gRPC.
Then we jumped into the enterprise world of Apigee. We used that traffic controller analogy to frame its role as a shield for those fragile legacy systems. And we broke down the vital difference between a quota policy, which manages the business contract, and spike arrest, which protects your infrastructure from those dangerous bursts.
And we saw how the platform enables real business growth through the monetization add-on and the self-service relief you get from the integrated developer portal. We also saw how fighting advanced bots forces you into the world of ML-driven security.
And finally, we landed on that critical choice of Apigee Hybrid, showing that when data residency is non-negotiable, the solution is to physically separate the cloud-based management plane from the on-premises runtime plane. The lesson, as always, is that your technology choice is driven by your constraints.
The platform has to fit the mission. Okay, so now that you have this really clear picture of Apigee Hybrid and the operational complexity you take on to keep that runtime on-prem, here's your final provocative thought.
What are the dramatic implications for both your capabilities and your security of going all in on a public cloud model like Apigee X, a model where all components, both the management plane and the high-volume runtime plane, are completely managed by the cloud provider? What kind of global scale might that unlock? And what new compliance risks would you have to accept when you totally give up that physical control you get with the hybrid model?
That's the deeper layer of cloud migration we should definitely explore next time.